Today we are going to look at the dictionary abstract data type. We are also going to see how binary search is done and what the analysis for binary search is, and then we will go on to hashing, see what is a hash table, how hashing is done, see the collision resolution techniques, and then in the next class we will follow up with more hashing techniques. A dictionary is an abstract data type that stores elements so that they can be located very quickly. So, one example that we can have of a dictionary is we want to store bank accounts, right. Now, when you store bank accounts, what is the key? What is the notion of a key? The notion of a key now is your account number, right. So, a bank account has lots of information associated with it, but you are going to access a bank account or data associated with that account by using the account number. So, the account number becomes your key, and as I said, an account stores a wealth of information, right. It could be your current balance, it could be the name and address of the account holder, it could be a list of transactions that you have done in the last few days, and so on and on, right. But when you have to access any of this information, you need the notion of a key. A dictionary is something that stores the elements. So, the element, when we talk of element, we will mean all this additional information, and when we talk of key, the key would be this account number, which helps us access the particular information. So, any application that wishes to operate an account or to do any kind of an operation on an account will have to provide the account number as a key. Without that, nothing is going to happen. So, it is basically an abstract model of a database. The dictionary is going to store these key element pairs, right. The key could be an account number. It need not be an account number. For instance, in the case of your suppose I had student records, then what would my key be? What would be the most natural notion of a key here? Your entry number, which is not an integer, right. You have characters in your entry number and so on, but anything that uniquely identifies a particular student or a particular account becomes the key. And one of the main operations that is supported is searching by key. What are the kind of methods that we have in a dictionary abstract data type? So, this standard container methods that we have seen for queues and stacks and so on. One is size, which tells us how many elements are there in the dictionary, is empty, whether the dictionary is empty or not, and elements, which returns to us all the elements that are there in the dictionary. Then we will have these query methods, right. So, given a particular key, find the element corresponding to this key. Now, in settings where you might have the same key associated with many different elements, and one could have such kind of settings, we will see examples of this later, then given a particular key, you want to return all elements who have that key. Yeah, you could have update methods. So, given I might want to insert an element E, which has a key k, I might want to insert that into my dictionary. I might want to remove an element with a certain key. I might want to remove all elements which have a key k, right, just what you would think as a standard thing. But now you should remember that there is the notion of a key, and that is crucial for help in searching, right. Without the key, it would be very difficult for us to search through this wealth of data, through this database. We will have a special element nil, which will be returned by an unsuccessful search. What does that mean? That means that if I am searching for a particular key and that key is not there, there is no element with that key in my dictionary, then let us say my procedures would just return a nil, right. This is some special element. Okay. One thing that we will keep in mind is that we only require comparison of keys for equality. So, given two particular keys, we are not going to say one key is less than the other, right, or one key is more than the other. This is not really required, because all you are doing is searching for a certain key. So, all that is required is, given two keys, you want to say whether they are the same or not. There is no notion of ek kisi se bada hai ki nahi, right. So, for instance, again for student records, I could have my key as your name, in which case there is really no notion of taking two names and saying one name is smaller or one name is larger than the other. Right? So, the only operation we will be required is comparing keys for equality, right. So, we do not need any order on our keys really. Okay, how can a dictionary be implemented? So this is the abstract data type, and then what we are going to do in the next few lectures is talk about how this particular abstract data type can be implemented. And we are actually going to see many different ways of implementing this abstract data type. You already have seen some ways of implementing this abstract data type. You could, for instance, use an array, or you can use a linked list to implement a dictionary, right? Can everyone think of how to use a linked list to implement a dictionary? Suppose I had student records, right? How would you use a linked list to implement this dictionary? Every node would have the key, which is the entry number, and all the data associated with that particular entry number, right? It's a very inefficient way of doing things, but it is a way of doing things.
But we said that there is no notion of a predecessor or a successor.
There is no notion of a predecessor or a successor. That is true, yes.
So how would we be connecting those? I mean, on what basis would we be connecting the nodes?
So your question is that if you were using a linked list, how would we organize it? That is up to you. You could connect them in a completely arbitrary manner. You know, the nodes could be in a completely arbitrary manner, or you might want to organize them some way. But you know, you could just throw them arbitrarily into the linked list, and that's fine. That's a linked list implementation. It's not very efficient, but it is an implementation. Yes. Right. So today what we are going to see is what's called a hash table, and in later classes we are going to look at binary trees, red black trees, AVL trees, B trees. These are all mechanisms, data structures to implement just this dictionary abstract data type. It's a very critical, it's a very important data type, and so we are going to be spending quite some time on this particular data type in these lectures. Right, in Java you have two abstract classes. You have an abstract class called java.util.dictionary, which lays out the specification. You also have an interface called java.util.map. Right, you can have a look at what the specifications are for these two classes on your own. Before I get more into dictionaries, so you understand what the abstract data type is, right? Before I get more into it, let's look at the problem of searching. Right? This is a small aside, but you will see why I am making this aside and how it will link up to the subsequent discussions we are going to have. So the problem of searching is the following: you are given a set of sequence of numbers. Let's say these are your keys in a database, anything, and I give you a single number. This is my query. Right? So for example, I could have 2, 5, 4, 10, 7 are the keys in my database, and I query is 5. What do you have to return? You have to return to me what is the position of this key in this database. Where is it sitting? Right? So index of the found number or null or nil. Right? So 5 is sitting at position 2, so you return 2. While here 9 does not appear anywhere here, so you return nil, saying it does not appear. This is the problem. Yeah, this is what we call searching. Let's see how we can do that. We are going to see a technique called binary search. I imagine all of you have seen this before, right? But we are in any case going to recall the technique and do an analysis of it. So the key idea behind binary search is divide and conquer, and this is the design technique that we are going to see in future classes also applied to different problems. Yeah. So what we are doing in divide and search is really to narrow down the range of elements in which we are searching for the query, the key. And let me take you through an example. Suppose these are the elements sitting in an array, right? And these elements have to be in a sorted order, increasing or decreasing, for binary search to work. Now suppose I am searching for element 22. What do I do in binary search? I'll go and look for the middle element, look at the middle element. In this case it is element 14, right? I'll compare 14 and 22. 22 is larger than 14, so that means that 22, if it lies in this database, would lie to the right of 14. Why is that? Because these set of elements are in increasing order. Yeah, everyone is okay with that? So which means that the element 22 has to lie between here and here. So we use these two variables low and high to indicate the range of the part of the array in which we have to search for our element. So, initially we had to search for the element in this entire array, but after looking at 14 we have figured out that we should now search for the element only in this part of the array. Yeah. So, now we are searching for 22 in this part of the array. Once again we are going to repeat the same thing, that is, go to the middle element, compare 22 with this middle element. 22 is less than this middle element. So, which means that 22 has to be to the left of this, which means that now we are searching for the 22 in this part of the array. Once again we go to the middle element, we search for, we compare this middle element with 22. 22 is larger. So, if 22 is there, then it has to be in this particular location, and it is there. So, we can then say that 22 is at this location and return this information. Yeah, you have all seen binary search before, so this is nothing new perhaps. So, I am going to write down a recursive procedure to do binary search. This is just pseudocode, and all of you can read and understand this very quickly, I imagine. What is being done? So, once again we had this notion of low and high. Low was the lower end of the range and high was the higher end of the range in which we have to search. So, the procedure call is A is the array in which you are searching, K is the element, the key which you are searching for, and low is the lower end and high is the higher end. Yeah. Now, what is the first thing? So, if low is more than high, then basically that means that you are invoking it with something wrong. So, you just return null, which says that the key is not there. Else you go to the middle element, which is obtained by taking the average of low and high, and check if the middle element is the key you are looking for. If it is the key you are looking for, then you just return. Recall that you have to return the position where you found the key. So, you will return mid. If the key you are looking for is less than the middle element, then you know that you have to search in the left part of the array. The left part of the array has a starting location low and its ending location mid minus 1. So, you are going to search in that, and this is your recursive call to that procedure. And if such were not the case, then you would come to this else, and in this case what do you have to do? You have to search in the right part of the array, which means mid plus 1 to high, right. So, this is how you can do binary search. So, it is a small piece of code. This is recursive. You can also write an iterative procedure for this. They are exactly equivalent, but I just, so that you know how to maybe go from a recursive procedure to an iterative procedure and you understand this thing very well, I have just written down an iterative procedure also for this. Now, what is happening in our iterative procedure? The low to begin with is 1, high to begin with is n. This is elements 1 through n, let us say, in an array, and we are doing the same thing roughly, except that we are now putting it in a loop, right, and updating high and low every time, right. So, after this first step, low becomes mid plus 1 because the element was larger than the mid element. So, the element was larger than the mid element, so low becomes mid plus 1, and when the element is smaller than the mid element, then high becomes mid minus 1, and we just go through this loop till we either find the key, in which case we just return the location where we found the key, or low becomes larger than high, yeah, in which case we would just come out of this do while loop and return nil. Yeah. Everyone okay with this? Any questions at this point? So, I have just shown you how to write binary search in two different ways. You can write a recursive procedure, you can write an iterative procedure to do the same thing. How much time does binary search take? Log n base 2, right? You all know that, but why is it that it takes log n base 2 time? Exactly, the size of the problem is halved at every step. So, the range of the items that we have to search in is halved after one comparison, after each comparison, right. So, if initially the range of the elements in which I am searching for my key is n, then after the first comparison it goes down to n by 2. After the second comparison, the range goes down to n by 4, and so on and on, right. So, after log n comparison, the range would go down to 1, and when the range goes down to 1, either it is that element or it is not that element, and you can stop. So, you will roughly require log n base 2 comparisons. Yes. Now, if you have an array implementation, that is your elements were sitting in an array, then you can go to whichever location you desire in constant time, right. So, then you can do the entire thing, each of these comparisons can be done in 1 unit of time in constant time, and so you can do the entire process in only order log n time. Yeah. When we do not write any base for a log n, we will understand in this class that it is base 2. Suppose the numbers in that array were not in sorted order. Okay. Here earlier till now we have assumed that the numbers were in increasing order. You can do binary search even if the numbers were in decreasing order, but if they were in sorted order you can do binary search. If they were not in sorted order, what can you do? Suppose you are still searching for a key k, right. There is nothing else you can do but to go through all the elements, go through the entire array one element after the other and compare your key against that. That's the only thing you can really do. Yeah. So, the worst case time then becomes order n, right, on an average also. So, if you are lucky, you might get the element initially at the beginning only of your search, but on an average you will get it, you know. So, if maybe the first time you got it at the very first position, some other element you searched, you got it at the third position. So, on average you are going to still spend order n time, right, and this is really the best you can do if the array is sorted. So, you can see there is a huge difference coming up already, right. By sorting, if you were to sort the elements to begin with, then you can search much more quickly, right. And this is a small pseudocode which is just saying that all you can do is run through the array one element at a time and compare your key against the element in the array. Okay. So, now that ends my aside on searching, right, and I am going to go back to my dictionary problem, and I am going to look at a setting where you are asked to implement, let us say, a caller ID facility for a large phone company, right. So, there is this company, and what it wants you to do is, given a particular phone number, it wants to. So, what happens in a caller ID facility? When a call comes in, based on the phone number, you can figure out the name of the person who is making the call. Yes. So, that is what the company wants to do. Given the phone number, you want to return the caller's name. Okay. Let us assume that our phone numbers are all 8-digit numbers, as is the case in Delhi, right. So, the range of phone numbers would be 10 to the 8 minus 1, right. That is 100 million, that is roughly 100 million phone numbers. Of course, the number of different phone numbers is much less than this, right. This is the range is 100 million, but maybe Delhi has only about a million different phone numbers, right. That is because not all numbers are present. So, there are n phone numbers, and n is much smaller than r, right. You understand the difference between r and n. R is the range, which is 100 million, because the phone numbers are 8-digit numbers, and n is the actual different number of elements in your database, and we want to do this as efficiently as possible. Everyone understands the problem? Okay. So, you can use an unordered sequence to do this. What does that mean? That means that suppose these were the phone numbers, I have not put down the 8-digit numbers, but let us say these were the phone numbers, you could just put them in a list, yeah, in any arbitrary order. And now, how much time does searching take? Order n. Does everyone understand why? Right, because you cannot do anything else but to traverse through this list, and in the worst case you might have to go through the entire list, and so it will take order n time to search for a particular phone number. So, given a particular phone number, if you have to return the name of the person, you will have to take roughly order n time to be able to do that, right. And this is an unordered list, right. So, there is no particular order. So, removing an element, So, how does one remove an element? Suppose a particular person decides to forego his connection, give up his connection, right. So, you have to remove that particular data record from this list. What would you do? You would once again search first. You will first search where it is and then you will remove it. Right. So, searching and removing, since searching itself is taking order n time, so removing is also going to take at least that much time, and you can actually, once you found where the element is, then you can just do some small modification to do the entire thing in order n time. Inserting. Why does inserting take only constant time? It is an unordered list. You don't really care where you are putting the elements. You might as well put it at the very first location. Yes. So, inserting takes very little time. So, it is not clear whether this particular implementation is good for this application, but there are certain applications in which this way of doing things is fairly good. And one such application is where you have to maintain log files, right. So, when you have to maintain some kind of a log file, for instance, any kind of transactions that are happening in a database, you try to maintain log files, so that if there is any problem, you can figure out, you can revert the transaction or whatever was done. Or for instance, in your systems, you would so for system administration, you would keep track of all the various activities that were happening on your system and maintain this and maintain a log of them. So, for log files, it is very rarely that you need to do searches or removals, but you need to add data frequently to your file, right. Every time something happens, a transaction happens, you need to add. So, insertions are very frequent, but searches and deletions are much rarer, and in that case this implementation is good, because insertion takes only constant time, right. So, you really have to see between these three operations, right, which is the operation which is being performed more frequently, to decide what type of a data structure to use to implement the abstract data, the dictionary data type. You could use an ordered sequence also, in which case, let us say the elements we have put them in increasing order of their key, right. Now, how much time does searching take? Log n. Log n, provided you had some kind of a direct access mechanism into this thing. So, used an array or some such thing which will let you go to whichever element you were looking for, whichever element you wanted to go to. Yeah. So, searching takes only order log n time. Inserting and removing will take order n time now, right, because if all of these were put in an array, then if I know, so since I have to insert them in, so if I have to maintain the sorted order, then I have to insert the element at a particular location. If I have to insert it at a particular location, I have to shift everything that is to the right of the element. Yeah. And so, insertion will take order n time in the worst case, and similarly deletion you will have to move it back. We have seen examples of this in the previous class.
So, how does inserting take order n? We have to search for the position first where we need to put the object.
Right. We first have to search. So, your question is, why does inserting take order n time? So, we have to first search for where the element has to be inserted, and once we know where the position is, then recall this is an array, all the elements are put in an array, right. So, we have to move, we have to create space there. And how can we create space there? We have to move everything that is to the right of that element, we have to move it one step to the right, right. And in the worst case, we might have to move order n elements to the right.
But we also take the order log n.
Yeah. So, what is order n plus log n? Order n, right. So, you have to recall your big O notation. So, order n plus log n is order n. Right. So, this would make sense when you have to do a lot of searching in your dictionary, but not so many insertions and deletions from a dictionary. There is one other way which will be useful for our subsequent discussion, and that is as follows. Let us say I take an array of size 10 to the 8, right, huge array, and then what do I do? Well, Ankur had a phone number of 96358904. So, I go to location 96358904 in the array and put Ankur's name there, or whatever is the additional information associated with it, I put that in that array at that location, right.
It's at that very position
at that very position, which corresponds to Ankur's phone number, right. Now, all operations insert, search and delete will now take only constant time. Is that clear to everyone? Why? I just have to insert a caller ID capability. What does that mean? Given a phone number, I want to know who is the person. So, given the phone number, I just go straight into the array at that location and retrieve the name. Given a phone number, I want to, let's say, I create a new phone connection. So, I take the phone number, I go to that particular location, I put the name of the person who got that connection. Similarly, if I want to delete a particular phone connection, I just go to that particular location and I remove the element there. Yeah. So, all operations take only constant time. Great, right? But what's bad with this implementation? We are wasting a lot of space. Yes. So, it is not that you cannot do all of these operations very quickly, you can, but here space is turning out to be an issue. Right. So, now we are going to use what is called hashing. Okay. We are going to use a hash table which will let us do the things fairly quickly. I have said order 1 expected time here. It will not take too much space either, and let us see what this idea is. So, what we are going to do is recall in the what was the problem with the previous example. In the previous technique we had 100 million phone numbers. So, we had to create an array of size 100 million. Yes, but there were only, let us say, 1 million users. So, most of the array was getting wasted, there was nothing in there. But suppose I could create a smaller array with, let us say, only 1 million locations in it and map those 1 million users to locations in that array. Right. So, that is what we are going to do. Let us say in a hypothetical setting there were only small number of users. I was only trying to keep the phone numbers of 5 of my friends, right, but I still wanted to do something fancy. So, I create an array of 5 elements, right, and what do? I take Ankur's phone number and I compute this value modulo 5, which is the size of my array. So, I get a number between 0 and 4, yeah, 0, 1, 2, 3, 4. When I compute this quantity modulo 5, I get either 0, 1, 2, 3 or 4, and depending upon what I get, I put. So, in this particular case, I would get 4. So, I put Ankur at location 4 in my array, right. So, I am not using too much space, and maybe I can still get away with constant time for insertion and delete, and let us see whether we can or whether we cannot do that. So, let me take another example just to make sure that you understand what the idea is. So, let us say the keys are now not phone numbers, but the entry numbers of students in this class, right. So, your entry numbers look something like this: 2004 or 3 or 2, and then you have these 2 characters, and then you have another 5 digits at the end of this thing. Yes, there are about 100 students in this class. Yeah, the range of this numbers is huge, right. This is, in fact, I do not even know what the range is, because I do not know what different set of values they can take. But I would like to create a table of size only about 100, because there are only 100 people in the class. Why should I spend much more space than that? And let me pick up a hash function. So, this function which I was using, which in the previous example was this modulo 5 function, is also called a hash function, right. So, I am now going to pick up a hash function which is, let us say, which does the following: takes the last 2 digits of your entry number. So, in this case 2004 CS10110 would get mapped to location 10. It just picks up the last 2 digits of the entry number, right. So, that is what I am going to do. I am going to take each one of your entry numbers, I am going to look at the last 2 digits, and I just have a table of 100 entries, a table of size 100, and I am just going to put you depending upon what the last 2 digits are.
What if you flash?
What if they clash? So, suppose I had another person with this entry number 2004 CS 50310. I do not know if they are there in this class, but there could be another person of this kind, right. Now, the problem is that these two are going to go to the same location number 10, right. We will come to this problem, but if this problem did not arise, then do you see that we are in a very great shape? Then you can do your insert, delete and search all in constant time, because it is very much like that array implementation that I showed you, right, except that it also does not waste all that space. Yeah. Okay. So, let us see what we can do with this problem, how we can address this problem. If two elements are getting mapped to the same location in our hash table, what is it? This is called a collision, right, and so we have to find a way of addressing this issue. So, how do we deal with two keys which map to the same spot in our hash table? So, we use a concept called chaining, right. There are many ways of addressing this issue, and today in today's class I am only going to look at the very first techniques, the simplest technique called chaining. We are going to do the following. We are going to have, this is my hash table. I am not going to put the elements in this hash table, but I am going to have a linked list starting at each of these locations, and I am going to put the elements in this linked lists in these, right. So, suppose this is my hash table had only 5 locations in it. So, maybe I was just using the hash function which was computing, which was taking the key and computing modulo 5 or some such thing, right. And so, if two keys were getting mapped to the same, to this location, 2 or more keys were getting mapped to this location, I will just keep adding them into this linked list. So, as you can see from this picture, it was the case that 3 keys were getting mapped to location 2 and 1 key was getting mapped to location 4, and there were no keys getting mapped to locations 1 and 3. Yeah. So, this does address the problem of collision, but what other problem does it create now?
Space again. Accessing the entries will not be, it will be a list, so we have to go through one by one.
So, while we have resolved the collision problem and we are not able to do things in constant time anymore, right. Worst case will become, in the worst case what might happen? In the worst case what might happen is that all the keys get mapped to one location in this hash table, and if all of them get mapped to the same location in the hash table, then your data structure reduces to a linked list data structure, which we know has a worst case time of order n for search, insert, search and delete. Insert is still constant time.
The data in this link, in the each box will contain both the identity and the phone number.
Yes. So, your question is whether each of the nodes in the linked list will contain both the identity and the phone number in the caller ID example, and yes, that will be the case. Each node will have both the phone number of the person, all data associated with the person would sit there. So, this is quick recap on how we are going to do the find, insert and delete of an element. So, for all of these 3 operations you have to do essentially the same thing. You have to use your hash function h to determine where that key is in this table, right. Now, we have seen 2 examples of hash functions. In one case we said we will just take the key modulo 5, and in the other case we said we just take the last 2 digits of the key. Yeah, but there could be many different kinds of hash functions, and in the next class we are going to see what are the different kinds of hash functions that people typically use.
Last 2 digits are same as modulo 100 only.
The last 2 digits can also be regarded as modulo 100. The reason I did not write modulo 100 was that was not an integer at all, your entry number. It had some characters in it. Yeah. So, you are going to use your hash function to find the position of the key in the table, and then you are going to go and, if you are doing a search or an insert or a delete, you are going to go and do that in that linked list associated with that position. Yeah. Now, there are options that you have here. you might want to maintain this list in a sorted order. You might want to keep it unordered, right. If you want to maintain it in a sorted order, then insertion is going to take more than a constant amount of time. If you want to keep it unordered, then insertion is going to take only a constant amount of time, because you can just insert it at the very beginning or at the very end of the linked list.
The end will be the order in key.
If you want to insert an element at the very end of the linked list, then you don't need to traverse the entire list to reach the end. You can always have another pointer which always points to the end of the linked list and use that to update. Although there is no reason why you want to insert at the end, but suppose you wanted to insert at the end, you could also do that in constant time always, right, by maintaining one pointer. So, we will have two pointers from here, one going to the front of this linked list and one going to the tail of this linked list, and use that pointer to add an element at the end of the linked list.
So ordering here is in what sense? Alphabetically of the name, in any sense we can do that?
You can do it in, so the ordering, if you want to keep it ordered, we are not saying that in the hash table you have to keep anything ordered. If you want to keep it ordered, you can do whichever, if there is a notion of order on your keys, you can use that notion to order the elements. So, an element with key k is stored in the slot h of k. What was h? H was the hash function, h of k is the value of the hash function. And what is this hash function doing? The hash function is mapping the universe of all keys, let us call that u, to slots of the hash table, right. So, if the hash table was of size m, so it is mapping, it is a function from u, the universe, to 0 through 1 m minus 1. We are going to assume for the rest of the discussion that the time to compute the hash function for any key, given key k, is a constant time, right, because quite often we just have to do some simple arithmetic operations to compute the value of the hash function. So, we are going to assume that it's the time taken to compute the hash function is independent of the number of elements in the table or any such thing.
So the choice of the hash function is arbitrary.
As far as the choice of hash functions are concerned, we are going to see in the next class what are good choices of hash functions, right. There is a lot of research done on this, and we will see what are the kinds of hash functions that people typically use. I just gave you two simple examples of hash functions, so as to motivate the concept. Okay, so what is a good hash function? This should be a good hash function. A good hash function is one which tries to distribute the keys uniformly over the table, right. It should not map all the keys to location 1 or location 2 or any such thing, because then there would be too many collisions. Your data structure would start looking more and more like a single linked list, right, and that is not what you want to have. So, you want to have a hash function which distributes things uniformly over the table, right. Why uniformly? So that each of the lists is small, right. So, an ideal hash function would do something like the following. It would take an element and let us say I have a table of 100 locations, it will pick at random one of those 100 locations and throw the element there, right. This kind of ensures that every location would have roughly the same number of elements, right. But this is not a hash function, what I just said. You can't have a hash function which takes a key and just puts it at a random location. Why is this not a hash function? Because when I am searching for the element, where am I going to go and look, right? I don't know what random location it had picked at that point. So, while this is an ideal hash function, it is not really a hash function, right. So, but for our analysis, we are going to assume such a hash function. We are going to assume that our hash function just essentially does the following, that it takes the element and throws it randomly, uniformly with the same probability in one of those locations of the table, right. We will call this the simple uniform hash function, and we are going to use this for our analysis. I will use another term which is called the load factor of the table, which is just number of elements in the table divided by the number of slots, the size of the table, yes, and we will call this load factor alpha. Any questions? None. Okay. So, what happens when we are trying to search and our search is unsuccessful, right? So, which means that I took the element, I computed the value of the hash function. I went to that particular slot in the hash table. I ran through the linked list, but I did not find the element. So, I went through the entire linked list and I did not find the element at all. Yeah. What is the, so how much time do I spend? I spend time proportional to the size of the linked list that I had to go through, right? Because I said computing the hash function takes constant time. So, you did not take any time to go to the right linked list, but once you went to the right linked list, you still have to step through the entire linked list, follow pointer by pointer till you reach the end. So, the time is proportional to the size of the linked list. And what is the average size of your linked list? Right? If there are n elements that I have thrown into my table and m is the number of slots, and if I had this nice hash function, the simple hash function which was essentially distributing things uniformly, then on an average you would expect that each linked list is of size n by m, which was the load factor of the table, right. So, the expected number of elements that need to be examined is alpha, and so the total search time, where I am using this 1 to denote the time taken to compute the hash function, is roughly 1 plus alpha, right. So, this tells you that, you know, if your alpha is, let us say, only a half, then, you know, the expected search time would be roughly a constant. Okay, this is expected under this ideal hash function. You can always create a bad hash function for which the time taken will be order n, right. I will grant you that. But if you have a good hash function, yeah,
it's actually just order alpha only, because one can be,
yeah, you can, of course. So, this I just to make sure that you understand that there is also a time that is spent in computing the hash function, I put this one here.
So, we wouldn't want a hash function which gives order n, then we don't need to use the hash thing at all.
We would not want a hash function for which everything is getting mapped to one location, right, because that is a linked list. Why would you want to do something like that at all, right. So, this is again brings us back to the same question. The efficiency of this data structure relies critically on the hash function you choose, right, and we will see, as I said, we will see what are good hash functions. In the next class, designing hash functions is much more of an art than a science. You have to really look at the data that you have to be able to design a good hash function around it.
So do we design like general hash function, or do we design it corresponding to?
When I am going to show you in your next class some principles behind hash functions, what kind of hash functions one should use, right. But there can be no theorems which say that, you know, this is the best hash function and you should always use this. What happens when we make a successful search, right? That was for an unsuccessful search, but when I make a successful search, what does that mean? I once again took the key, computed the value of the hash function, went into the appropriate linked list, and then I am now walking through that linked list. But I do not have to reach till the end of the linked list. At some point in the middle itself, I am able to find my element. Yes, right. Now, how many elements did I have to traverse in this process? The position at which it was found, exactly. But how do I know? So, what is the expected time I would take overall? By expected time I mean, you know, if I searched all the various elements that are there in the database, what is the average time I would take to search all those n elements that are there in the database, right. So, let's argue it like following. You can have many different ways of arguing it, but let's do it in the following way. So, suppose I was searching for the element which was the ith element which was inserted into my database, right. Suppose the element that I am looking for, the key that I am looking for, was inserted into the database, inserted into the hash table when there were only 9 elements, right. And so, this was the 10th element that was inserted. So, if it was the 10th element that was inserted, the expected length of the list in which it was inserted was 9 over m. That is what we argued just now.
M is the number of rows in the table.
Exactly, the number of slots. M is the number of slots in the hash table, right. So, in the case of a successful search, the expected number of elements examined is one more than the number of elements examined when that particular element was inserted. When the 10th element was inserted, I equals 10, let's say, when the 10th element was inserted, then I went through the linked list in which the element was inserted and appended, let's say, that element at the very end. So, I had to still compare that element with all the various elements. Yeah. So, when I insert the element, it's basically, it's the same as saying that the number of comparisons I have done is one more than the number of comparisons I would have done in an unsuccessful search.
Do we need to insert at the end of the list?
We have to go through the entire linked list when we are inserting. Why do we have to go through the entire linked list when we are inserting? Just to make sure that the element is not already there. So, we in any case have to make sure that it is not there, and then, so we have to go through the entire linked list. So, we might as well insert at the end. We could also insert at the beginning, but it is the same thing. Right. So, one could now have an analysis which looks like the following. This is not very critical, you can all prove it in different manners, but now what I am doing is I am looking at the elements 1 through n. There were n elements in my database. When the ith element was inserted, then the expected time I required, then when the ith element was inserted, then the linked list, the expected length of the linked list at the end of which it was inserted was roughly I minus 1 by m. Right, and this 1 is, let's say, for our hash function computation. So, this is roughly the time, the expected time required to insert the ith element. And now we are just summing this quantity up over all the n elements and taking the average, right. And if you just go through this math, you get something like this following. And if many of you could have figured this out on your own also, right, the average time would be roughly the length of the expected length of the list divided by 2. Whenever we are doing average time computations, for when I said, take a linked list and what is the average time to search for an element, you said, well, I might have to go till the end of the linked list, or I might find the element right at the beginning. On an average, I'll take about half the length of the linked list. So, you are seeing a similar kind of a behavior here. This is a very low order term, so you can just ignore that. So, what you're seeing is something like 1 plus alpha by 2. So, we don't really have to go through this math, but you can also follow it. This is more intuitive. One could just say that the average time for a successful search would be more like 1 plus alpha by 2, right. So, again it's order 1 plus alpha, right. This 2 is not important. Yeah. So, both for successful and unsuccessful search, we are taking a similar kind of a time, right. So, what should alpha be? What should be a good choice of alpha? Right. We would like to keep the size. So, recall that alpha was the load factor of the table, the number of elements in the table divided by the number of slots in the table. So, if I pick the size of the hash table to be roughly the number of elements that I am going to be inserting in the hash table, then alpha would be roughly a constant, roughly 1. Yeah. And so, all your searching, insert and delete would now take constant amount of time, in the expected sense. In the expected sense, I mean when you have this kind of an idle hash function, which you can't really have. Any questions till this point?
So, what if we don't know how many elements we have to insert?
Okay, what if we do not know, your question is what if we do not know how many elements we have to insert? Then what should we do? What size of our hash table should we start off with? Any suggestions on that? Pardon? Exactly. We used a concept of growable stack, right? So, the same idea is used in many of these data structures. You start with something small, and if the number of elements that you are inserting becomes so large that the sizes of the linked lists become very large, then it's perhaps time to move the entire set of elements into a larger hash table.
Then you have to convert every delta with another new hash function.
Right. So, either you have to compute a new hash function, or we will see how to modify these things, how you can do a small modification to the hash function so that you can now put it in the larger table. Right. So, that one should design one's hash functions keeping this in mind, that you might have to go from a smaller table to a larger table to an even larger table and so on.
So, if the number of hash table slots were to be proportional to number of elements, Won't there be a space problem?
If the number of hash table slots was proportional
To the number of elements.
to the number of elements.
Won't there be a space problem?
Your question is, won't there be a space problem if the number of hash table slots was proportional to the number of elements, right? So it depends upon what this big O is hiding here. What I'm saying is, let's say we pick the number of hash table slots to be equal to the number of elements, right? So there's no problem here. This hash table, suppose n was 1000 and m was also 1000. This hash table can accommodate any number of elements. It's not just that it can accommodate only 1000 elements. Why is that? Because in the linked list you can attach any number of elements that come, right? It's just that the performance of the hash table would deteriorate if you had 10,000 elements coming, because then each linked list would become of size 10 roughly, maybe more, maybe less, right? But on an average the linked list length would be 10, in which case it makes sense to maybe move to a larger hash table, right? If you know that the number of elements is only is 1000 and you create a hash table of size 10,000, right, then there is a wastage of space. So you should always start with a small hash table and if need be grow it, rather than starting with a very large hash table and having wasted space. Are there any other questions?
So can you explain that successful search thing again?
I will end this class here at this point, and any other questions I can take offline. Right. So in today's class we saw binary search, which many of you had seen before. We also saw a little bit of hashing, and we saw what the dictionary abstract data type is. So in the next class we are going to continue with hashing, see concepts of good hash functions, and see other ways of resolving collisions. Okay.